Thank you, Rebecca. So as Rebecca noted, today we're going to kind of go into an aquatic herbicide 101. So we'll talk about some modes of action, how they're used, sort of how they perform and function in the environment. I'm not going to spend too much time on my background. I believe that Rebecca covered it. So with Herbicide History 101, we'll talk about how did we get to where we are today. And what I mean by that is what do we have available to us as aquatic and both riparian managers. We'll dive into some herbicide mode of action, so how some of these chemistries specifically work in the environment. Talk briefly about invasives in Montana, and then if we have time for questions, we'll take those. Just a bit of housekeeping here. Nothing that I mentioned by rates or specific chemistries today is a set in stone recommendation. So if you have any questions on how to manage your site specifically, please reach out to any one of us. Also, this presentation will be made available as a PDF. And so if you are bored at night and you can't sleep, it's a good one to review. So we'll talk about how did we arrive with pesticides. And the first thing I want to talk about is global agricultural food production from the turn of the century, until the early 2010s. And you'll note that, it was fairly static up through the 1930s. Now, this is interesting because it was in 1913 that two German scientists, Fritz Haber and Karl Bosch, respectively, invented a process to produce nitrogen artificially. Before that, it was extracted from soils. Now, unfortunately, you would have thought that this would have been directed into agriculture directly, but they instead put it into weapons, which then went into World War I. And you'll note that food production really didn't change until about the mid-1940s. And so when I'm presenting to a live audience, my question always becomes, what happened in the mid-1940s that could possibly change food production rates? And honestly, that really came from 1946. We had the first commercial production herbicide, and that was 2,4-D. But 2,4-D actually came from the military. So after World War II, we had an ocean of 2,4-D left over, which was used as a defoliant in World War II. Post World War II, we had all these stocks left over, and this is what it became. So you can actually review how Union Carbide, or a chemical paint company, became Dow DuPont, and all the way back in 1941 was the first patent of the use of herbicides and 2,4-D. And so it was known as weed done in the trade. Now, bear in mind, this was also the period of time where there were some interesting publications on farming in general. And doctors were making some interesting recommendations to their clients, and children's books, if you recall. So the other point here is that the first herbicide, and this question always gets brought up, the first herbicide was not salt. And we've all heard of salting fields. Being a scientist, I was kind of interested in how much salt would you actually have to put on a field to kill crops. And that works out to be about 460 pounds of table salt per acre to get the effect that you're looking for to kill plants. Interestingly enough, it was the Roman Emperor Diocletian. He set the price of salt at maximum of 100 denarii per 46 pounds of salt. It's interesting to note here that the average soldier at the time was paid 3 denarii daily. So if you do the math, it would take 57 days of work for one guy to afford enough salt to effectively kill off half an acre. So it's highly unlikely that if you had something as valuable as salt given to you and somebody told you to throw it on a field, I have a feeling that a lot of that would not wind up on the field. Other interesting thing that I like to point out here is that people have been complaining about their jobs since way back. So something that is hardly new today. Now, when we start talking about the world of aquatic herbicides, it helps to understand the greater context. And herbicides in general, there are about 35, 36 modes of action or classes as of 2024. So the classes, there's about 300 distinct modes of action. And the first obviously was 1946 with that 2,4-D, and the latest is fluoroperoxidine benzyl. One of our later series speakers will probably talk more about that active ingredient. If we chart out when these herbicides were invented, the period from 1960 to 1980 saw a lot of herbicide development in the world. And in the world of aquatics, our flagship molecule, fluoridone, was first invented in 1973. Further looking at aquatics, topramazone, which is an HPPD inhibitor, came out in 2005. We have glyphosate that quickly went into aquatics, and a few other active ingredients. But it's important to note that all of the herbicides that we have available to us today ultimately have first come from the crop side. And that's because of the cost of registration and the timeline of registration. Today in America, it takes about 10 to 12 years to bring a new herbicide chemistry to market, get it through registration and the regulatory hurdles. That cost is anywhere from $160 to $180 million over that period of time. The point here is that we are highly unlikely to have more herbicides brought into the aquatic market space on anything more than a decade-long basis. So when you hear folks like myself talk about product stewardship, herbicide rotation, mode of action, what we're trying to do is preserve the toolbox that we do have available to us. So here are the auxin mimics. 2,4-D was 1946. Out here we've got dicamba, aminopyrrolid, and then fluoroperoxidine, which was invented in 2017. That is the latest mode of action that we have seen in aquatics. Now, the first case of herbicide resistance was documented in the 1950s. And today we have species such as water hemp that are known to be resistant to up to 6 classes. So in aquatics, we have been graced with a period of relatively few cases of resistance development, but they do exist. And so again, as managers of ponds, lakes, reservoirs, we do want to be careful that we utilize the best technologies out there, and we utilize them intelligently so we don't lose these tools. Now, I've showed you the chart that kind of gives you the overview of all herbicide chemistries that are out there today. But when we move into the world of aquatics, that toolbox becomes very small. In the world of aquatics, and I'm talking for all aquatic uses, we have about 11 different modes of action available to us. And we can break these up as to how they work. The first group would be called the contact herbicides. And so these are very fast acting. You put them out on plants, and generally within 24 hours, you're going to see the results. Next, we have the transitionals. Now, these are our growth regulators. You've heard me talk about 2,4-D all the way up to fluoroperoxidine. This one is known as Missoula in the marketplace. These are all systemic growth regulators. Now, I have them grouped by transitional because they are fast acting, they are systemic, but the results that we get from using growth regulators are usually somewhere in between a true systemic and then a contact herbicide. With regards to the systemics, these are herbicides that we put on plants, put on weeds, and generally it's going to take 7 to 14 days, sometimes longer, for you to see the effect. Now, the effect on the plants is immediate. We'll talk about that. But generally, with the way that these systemic herbicides function, it takes some time for the plant to start showing injury. Glyphosate is the poster child here. You'll know this is Roundup. And put it out on plants, it generally takes about 5 to 7 days for you to see those results. But truly, the plant is impacted within about 24 hours of being treated. We'll talk about that in a minute. I talked about our toolbox. If I look at this toolbox available for aquatics, and now I want to treat ponds, or lakes that might be used for irrigation or irrigation canals, these are the only chemistries I have available to me for that. So again, as your use pattern narrows, your toolbox is narrowed for you. Now, I talked about contact herbicides. These are generally used for fast activity or burn down, as we might call that. I noted that the symptoms generally are very fast to appear. The activity is usually going to be limited to the parts of the plants that you have sprayed. And so if you are treating annual plants, contact herbicides can be effective. If you are treating biennials or perennials, thistles, purple loosestrife, which we'll talk about later, those are generally not going to respond very well to contact herbicides because they usually have enough energy reserves to reproduce and continue growing. Now, with your contact herbicides, the size of your plants is very critical. So obviously you want to go out when they're small as opposed to when they're big. And some of the target species that we may go out after have defense mechanisms like hairy leaves or waxy surfaces. So you do need to take that into account. Now, another interesting note with your contact type herbicides is that, I call it the Quentin Tarantino effect. You spray a plant, and if it is susceptible to this herbicide, you're going to see, violent and sudden reactions to this on the part of the plant. So if we look at flumioxazin, flumioxazin is a contact herbicide. It's in the family of PPO inhibitors or protoporphyrinogen oxidase inhibitors. What this does in the plant is prevent the formation of this enzyme, protoporphyrinogen 4 oxidase, which then eliminates the plant's ability to step down sunlight energy for photosynthesis. So basically, we're forming the singlet oxygen, which is a free radical in the plant. It does all kinds of awful things, peroxidates lipids, breaks cell membranes. The plant really is not happy with that. If you spray contact herbicide on broadleaf weeds, this is what your typical symptoms are going to look like. A little spray droplet, mimic chlorosis, and then obviously, pretty quickly after these symptoms appear, the plants are going to die. Diquat. Diquat is another one. Now, this is a photosystem 1 inhibitor, but note that even though we have a different mode of action, ultimately we are still forming those free radicals. So the reason we're always drinking, blueberry juice and pomegranate juice, we're trying to get those free radicals out of our own systems. Same thing here. Diquat, forms these free radicals in plants. Sunlight energy can't be stepped down anymore. We get all kinds of free radicals forming. Again, contact herbicide, symptoms on leaves, little droplets. You can see where the spray droplets actually were landing on this leaf. Very quickly, the plants burn down, and obviously right after this, they die. Now, this is in contrast to the systemic type herbicides. Now, systemics, you're generally not going to utilize them on annual weed species because you can effectively manage them with lower cost contact type herbicides. But for your biennials and perennials, so again, thistles, those sort of species, systemics are the way to go. Now, as I mentioned, the symptoms are usually going to be slow to appear, so 7 to 21 days, as opposed to 1 to 3 days for contact herbicides. The activity with systemics generally moves throughout the plants with a focus on the reproductive structure, so the roots, the rhizomes, tubers, that sort of thing. These move throughout the vascular system of the plant, so the plumbing of the plant. And again, weed height is critical even with your systemics. These can be used in combination sometimes with contact herbicides to speed up that apparent activity, but you do need to be careful because some contact herbicides are antagonistic to your systemics, meaning they act so quickly on the contact side that the systemic doesn't have a chance to move throughout the rest of the plant. Again, at the end of the day, with your systemic type herbicides, you should expect to see sort of slow lingering demise of plants, but you're generally going to kill the whole plant, which again, with biennials, perennials, is the effect that you're after. So I mentioned fluoridone earlier. You would know this as Sonar probably. This is a phytoene desaturase or PDS inhibitor. These are known as the bleachers. And what do these bleachers do to the plants? Well, they basically prevent the formation of your secondary pigments. So you remember these are the pigments that we see in the fall, the xanthophylls, the carotenoids, the yellows and the oranges. Those pigments play a very important role in photosynthesis, in stepping down that sunlight energy. Think of it as sunburn on the plant. If the plants can't produce these secondary pigments, what you'll tend to see are these white leaves. This is very indicative of fluoridone treatment. And it should come as no surprise that, without the ability to step down sunlight energy. Again, we're forming these free radicals in plants. And if you want to guess what happens next, they die. Now, glyphosate. Glyphosate's an interesting one. You know, this is Roundup. This is an EPS-PS inhibitor. What does that mean? It actually prevents the formation of aromatic amino acids in plants. And aromatic amino acids do all kinds of things for the growth of plants, from protein synthesis, metabolite production, all kinds of things. Now, the plants are going to have an energy reserve in their rhizomes or their roots. So if we spray a plant with glyphosate, while glyphosate is going to move throughout the plant within 24 hours, the plant has some kind of an energy reserve usually. And so it might take a while for these effects to show up. You know, smaller plants think they have a less of an energy reserve. The symptoms are going to show up faster. Well-established plants, cattails, Japanese knotweed that have extensive rhizome systems, it can take some time for these to show up. So we prevent the formation of these aromatic amino acids. Again, it takes some time to see the chlorosis, but after a while, the plants just generally look unhealthy, usually within 14 to 21 days later. Anybody want to guess what happens? One more systemic herbicide. This is a mazamox. So interestingly, similar to glyphosate, this one prevents the formation of amino acids, but the ALS herbicides prevent the formation of branch chain amino acids. So a totally different group of amino acids, but ultimately the same effect, right? Plant just generally looks unhealthy after a period of time. It's really not reproducing very well. Again, 2-3 weeks in, they die. Now, when we talk about effects of the environment to efficacy of treatment, there are a few concepts that you need to be aware of. And so first, we need a molecule that has activity on our target species. So here I'm going to pick sonar. Next, we need a label that is approved for use in your intended use site. So it'll say right on there, ponds, lakes, reservoirs. You need to have the approved use site directly on your label. Then you need a concentration in the body of water or on that leaf surface that is effective to manage that species. And this changes with species and it changes with herbicides. You know, fluridone is very effective on milfoil at very low concentrations, 5 parts per billion. If I'm trying to manage northern water milfoil, a different species, I might have to take that rate up to 20 parts per billion. So this gets into this concept of concentration and exposure time. Maintaining that effective concentration over a period of time, that's your exposure time, to get the control that you're after. And every site is different, but this is how we determine how we're going to treat a pond or a lake. Now, it is really important as managers or going after aquatic or riparian species to know where you're likely to see these species and also what species are likely to be out there. And it's important to note here that most of our invasive and noxious species in the state of Montana are going to be found in, on, and around aquatic or riparian systems. So know your risks, right? You can't just pick any herbicide and go out after a plant because somebody told you or you heard somewhere that that was a good option. When I'm talking about environmental risks, I'm talking about non-target impacts. So here we had impact from a treatment in water that affected a sugar beet field up in Canada. This is not a good day. You don't want to see this. This was a site in Colorado where a lake applicator, not myself, was treating a lake that was used for irrigation. And they used fluridone. So you can actually see on the pictures on the right-hand side and that lower right, the leaves are turning white. That's very classic fluridone intoxication. And unfortunately, in this site, because fluridone takes so long to manifest its symptoms, by the time anybody noticed what was going on, the damage had been done. The fluridone was out on these plants. It was affecting their growth habits. And unfortunately, this applicator wound up buying a lot of replacement vegetation. You know, operational risks. Choose the wrong pesticide in an irrigation canal, and you're not going to get the results that you want, and you're going to have to go out and clean that up. And this can be anything from extensive time behind an excavator to overflowing burns and extensive infrastructure damage, as we saw in Idaho on the lower right-hand side. So I'll talk to you briefly about, again, the applicator's toolbox, some special considerations for some of these species. But first, I want to note the effect of water hardness. Now, in the state of Montana, we have all types of water out there, from very soft in the alpine high mountain regions to very hard in eastern Montana. Note here that the harder your water is, that the harder it's going to impact a lot of the herbicides that we've already talked about today. Glyphosate, 2,4-D, Flumi, these can all be antagonized by hard water. Copper is very impacted by very hard water. So you do want to know what kind of water you have on site, and there are numerous ways of checking your water hardness. Many people don't do this, but if you are trying to treat, this is a question that I would likely ask you as a site manager. Water pH is another one. Now, if you're putting pesticides directly into a body of water, there really isn't much you can do about water pH. But if you are spraying around your home, if you are spraying on ditch banks or spraying somewhere outside of the water, your spray tank water pH can have a huge impact on the efficacy of your treatment. And so I grabbed this slide or this graph a few years ago. I wish I remember who presented it. But these guys, the two lines, the blue line is just a full rate of Roundup. I believe it was used on foxtail. And if you follow that blue line across, it should come as no surprise that within about 7 days, we started seeing impact on the treated species. 14 days in, we were about 70% control. And within 3 weeks, we were approaching 90% control. They took that same treatment, same target species, and they put it into hard water in their spray tank. That is the green line. And if you follow the green line across, you'll note that by 21 days, we had lost almost 40% control. And so, as a technical specialist in the field helping my clients get better results, the first thing that they're going to say happened here was that they got a bad formulation. Fair enough. Sometimes they'll say that the job just wasn't done right, or they have resistance. And we've all heard resistance, particularly in the cases of Roundup. But I truly believe that many cases of poor herbicide performance in the environment are actually due to poor application methodology. And this slide shows exactly that. I had a client in Idaho who took me up on this, and they sprayed a site, and these captions are actually flipped. My apologies. The picture on the left-hand side, they sprayed Roundup in a ditch. They were just trying to get vegetation burned down. They did not adjust spray tank pH. And so you can see that 5 days in, we are seeing some effect. Those plants are turning a little bit yellow, but by and large, they're still pretty green. Same site, same applicator, same pesticide, but they adjusted water tank pH, brought it down, and that is the picture on the right-hand side. And 5 days in, you can see the difference in control they're getting. Again, this is absolutely a site that if we hadn't been paying attention, they may chalk up to resistance as opposed to just bad water tank pH. Going into the state of Montana, we've got 47 species listed as invasive, and these are classified as priority 1A. These are species that do not have any presence or very limited presence in Montana. We'll talk about one of these species. Priority 1B, these are again species that have very limited impact, and these do require eradication, containment, and education of the public. Priority 2A are common, but in very isolated areas. 2B, these are abundant and widespread in many counties, and we might just be going after management here as opposed to eradication. And then priority 3, these are just regulated plants. We'll talk about hydrilla as an example. So with one of these species, star thistle, this is one of the 700 members of the Centaurea. I referred to them as picker bushes growing up. This is an annual, biennial species. It can grow up to 6 feet tall, but generally it's about 2 to 3 feet tall. It emerges from a rosette in year 2. So you get that thistle-looking rosette on the ground in year 1. Year 2, it bolts from that rosette and sets its flower. And if you're managing a site like this, which I believe is in California with yellow star thistle, and it has already flowered, you're already missing the boat here, right? Now we're just trying to prevent seed set on these species because they're done after this season. So when you want to manage a species like star thistle is when it's in that first year rosette stage. Um, the sharp spines of star thistle can put grazing animals off of hay if it's present in it. It can be toxic to horses, but generally horses aren't going to eat this species unless there's absolutely nothing else out there for them to graze on. The seeds may have a plume or they may not. Yellow star thistles may have plume, they may not. Important note here is if you look at that flower in the bottom center, the yellow arrow is pointing to it. If it doesn't have spines on it, it's a knapweed. If it does, it's a star thistle. So easy identification. And again, these are widespread all across Montana. Dalmatian toadflax. Here's a picture of yours truly holding some over in Wyoming. This one is introduced and it's highly common, or very common. It's got bright yellow flowers, very heavy rhizome system. So if you look at that picture, this plant that I'm holding is actually, that is a single season seedling. And you note that those roots are almost 3 feet long. This is a plant that established itself in a river floodplain post-spring runoff and was able to grow in a rhizome system almost 3 feet long. So this plant, once it's established, is very hard to get rid of. The flowers are usually present from June through August. I will say in my experience that they're kind of done flowering by the end of July, particularly if we're having a dry summer. But if you start seeing yellow out on the sides of the roads and it's not mustard, it's probably toadflax. It's very common on roadsides, frequently disturbed areas, and just areas with generally poor soil. It may be poisonous. It may also be medicinal. Your mileage may vary. Purple loosestrife, we've probably all seen this one and not known it. It was introduced in the 1860s. I believe it was first found in the United States up in Lake Ontario. It actually came in from Europe in ship ballast that was then dumped. It's very widespread, extremely bright purple flowers, really pretty. It's got very extensive rhizome systems, so those are those reproductive structures underground. This one flowers from July through September. It's very common on roadsides, wetlands, frequently disturbed areas, also poor soils. You may confuse this with our native fireweed, but if you look at the two pictures on the bottom, fireweed has a very dispersed flower head on it. There's a lot of air in between each individual flowers, whereas loosestrife has a very tight central bolt coming up through the center. And so if you see that tight purple bolt growing in some wetlands, it's probably going to be purple loosestrife. Canadian waterweed, or Elodea. Now this one is native to the lower 48. It is invasive in Alaska, which is interesting. It's got very thin stems, generally 1 to 3 meters long, typically bright lime green in the water. The leaves on this one are smooth, so if you run your hand down the stem, it's going to feel slimy smooth. It's not going to have any kind of roughness to it. Mid-season, late season, so June, July, August, you might see small white flowers on the surface, but that's not really a good identification feature. The easiest one is to break that stem and look down on top of it. If it's got 3 leaves and 3 leaves only, it's Elodea. Now this one commonly overwinters as an evergreen. However, in the wintertime and early spring, it's usually kind of brownish, yellowy colored in that top right picture. But when it's vibrant and healthy in a water body, it looks like lime green. This is a picture. It's just kind of interesting out of Alaska. U.S. Fish and Wildlife, we were involved in an eradication project up there. As I mentioned, it's invasive in Alaska. They drilled down through 3 feet of ice trying to get sediment samples from a lake, I believe it was. And interestingly enough, they were greeted with bright green growing Elodea under 3 feet of ice. Not that this is unique to Elodea in any way, but it just kind of shows that many aquatic vegetation or weed species that we would deal with really don't need much in the way of nutrients or sunlight to grow, to the point of becoming a nuisance. Now, hydrilla. Hydrilla can be confused with Elodea, but the easiest way to key it out is that it's not known to exist in Montana yet. It's got thin stems like Elodea, 1 to 3 meters long, typically bright green. However, the leaves of hydrilla have toothy margins, and so again, if you run your hand down that stem, they're going to feel rough. It won't poke you like a thorn or anything, but they are spiky on the sides. The leaves on these stems can be anywhere from 3 to 10. So if you recall, we talked about Elodea always has 3 leaves. Hydrilla can have 3, but sometimes it has more. So as you look down that stem, that's another way to key it out. Now, the question always comes, can we dredge these out? Can we harvest these without having to use herbicides? And unfortunately, no. The reproductive structures of many of these species can occur up to 3 feet deep in the sediments. And so unless you are dredging out 3 feet of sediment from your lake, and even then it's probably not going to completely eradicate it, dredging really just winds up creating more potential fragments than is effective. Next, we've got milfoil. Now here I'm talking about northern milfoil, which is native. This one is commonly encountered. Thin stems with little leaflets. You can see a leaflet in the lower right picture. Again, it does set flowers mid-season. They can be little yellowish, they can be pink. The stems typically turn pink on this plant when it's mature, so July. Key feature to identify this one is that the leaflets are moderately dissected. And so if you count those little leaflet pairs, you'll have less than 14 on there. Whereas milfoil, Eurasian milfoil, the invasive, has more than 14, usually I think 27. Now, this species can hybridize, and it can hybridize with the invasive. So at this point, while leaf keying out can be an effective means of identification, because of the prevalence of hybrids, you almost have to send this one off for genetic analysis if you really want to know, the best rates to manage this one. Thankfully, Eurasian milfoil, as I mentioned very early in this presentation, responds very well to very low rates of the herbicide fluridone. And so we can go out there and have very limited non-target effect when trying to manage this species. With that, I believe we have a few minutes for questions if there are any. Again, if you have any questions outside of this presentation, please reach out and ask. Send me pictures. I'm happy to kind of work up a program with you that would help you control the situation at your site. Rebecca, you'll have to tell me if anybody actually has questions.
Great. Thank you so much, Andrew. Yeah, if anyone in attendance wants to ask any questions, just use that box